Hello? Are you ready to see some kind of service mesh stuff? Okay. Thank you very much for coming to this session about, service mesh patterns, or if you will, some kind of features that you can use in your microservices architecture if you are using Istio or service meshes in general. And my name is Alex Soto. I work in Red Hat, contributors of several magazines, and for today it's really important because there is a raffle. Also, if you are you are here in the session, there is this discount code. Well, no, it doesn't work. It's that 40% of discount of any product of Manning. So you can use this code, or even if you want, you can get a raffle for 2 electronic books of testing Java microservices, which I am the author. And the only thing that you need to do is just follow me on Twitter with a picture of the session. We mention me and GeeCON, and then I will send you, if you are the winners, I will send you the codes to download for free the book. So if you have any question, I know that there is an application that you can use, or if you want, you can just raise your hand, and I will try to answer your question at time. You don't need to wait until the end. So some years ago, now it seems ages, we developed something like this, right? A monolith. Everyone knows how it looks like, right? Although internally it's quite different. You have modules, and inside of each of these modules, we still have components. But 2 years or 3 years ago, we decided that it would be a good idea to start breaking down this monolith into something that was called microservices architecture. So we just spread all these components and modules across a network. So basically, you are, creating a mesh. This is what's called a mesh, which is several different pieces of software interconnected by the network. And you can see that now things are becoming more and more interesting. Of course, each microservice has their own database. Some have databases, others not. And also different or multiple points of entry. And there is not only one piece to entry to a service, but you can, for example, if you are an administrator, you can enter to any part of this microservice. But of course, at the very end, microservices, it's distributed computing. You have a service A running inside the JVM and inside an operating system that does a network call to service B, that does a network call to service C. At the end, it's a distributed computing as we have done many, many years before that. The problem is that when we start splitting or monolith into a microservice architecture, we as a developer think that it's like a memory call. So when we have a monolith and we have our component A that calls component B, what we are really doing is just doing a memory call. And then we say, okay, when we was a monolith, we are doing a memory call, and now we are just doing a network call. But it's exactly the same. And the problem is that this is the fallacies of distributed computing. That thinking in that way, it's wrong. Basically, you as a developer might think that the network is reliable, but we know that it's not. The latency is 0. The bandwidth is infinite. We always think that, okay, we can start doing calls to the network. Doesn't matter. Hey, I want to send you 1 gigabyte of a file through the network. Okay, send it. Doesn't matter. And it's not like that because the bandwidth is not infinite. The network is secure, and there has been a lot of attacks, not from outside of the architecture or outside the cluster, but within the cluster. So any attacker can gain access to one of these services and then attack the rest of the services. So as you can see, the network is not secure. Oh, sorry. And also, the topology does not change. There is only one administrator. The transport cost is 0, and that the network is homogeneous. These are all the things that we think when we are developing distributed computing system that we need to try to avoid. But let's think about one specific problem. What's happened when there is a downtime in the middle of the mesh? So it's just one service that starts failing. Now, it's not only this service that is failing. It's all the transitive services, all the services that are calling this one that are failing as well. So now instead of having one specific problem, we've got a problem spread across all the mesh. So as you can see, done properly, networking is an heroic art, right? So it's not easy as a memory call. For these reasons, Microservices implements one thing that I call the cross-cutting concerns of microservices, which looks something like that, where you have your service that can be implemented with any language, Quarkus, Vertex, Spring Boot, or Go, or JavaScript, and then there is a lot of, let's say, cross-cutting concerns that has appeared because we are using microservices architecture like discovery, invocation, elasticity, resiliency, pipeline authentication, logging, monitoring, and tracing. All these features are there because we are using the network. If we are just using our monolith application, or we are not using network, then you don't need anything of these features. So you can see that, okay, this is a disaster because I need to deal with all this stuff, or you can take it as an opportunity. So if you are, for example, using Kubernetes or OpenShift, OpenShift is the let's say, Kubernetes for Enterprises, which is an open source project from Red Hat. And it's a Kubernetes after all. It also covers all these, or most of the cross-cutting concerns like discovery, invocation, elasticity with the concept of scale up and scale down that we have with Kubernetes. And then if you are using OpenShift, you still have the pipeline because, for example, with OpenShift 4, we are using Tecton and Jenkins to create the delivery pipeline, and the logging and the monitoring, which is quite complicated with microservice architecture, are also solved. And the rest, well, usually we do something like that. We just implement our services with all the remaining parts. I mean, maybe you are using Istio, or you're using the microprofile specification for fault tolerance, or for matrix, or for tracing. I mean, at the end, it's like that you put some jars, if you're in the Java ecosystem, inside your class path to resolve all these kind of problems. But this ends up with an amount of bloated code because you end up by doing copy-paste from service A to service B. I know that nobody does copy-paste, never, but yeah, so you end up by doing copy-paste, promoting the errors across all your services. So how about implementing all these cross-cutting concerns at infrastructure layer? Because remember that we need to implement all these cross-cutting concerns because now we are in a microservice architecture with the network there. So how about putting all this inside the network? And this is exactly what the service mesh does. A service mesh is a dedicated infrastructure layer for making service-to-service communication safe, fast, and reliable. And as you can see, basically what a service mesh is doing under the covers is intercepting all the traffic that is happening between the services and then manipulating. And since you can manipulate, we can do whatever we want with this traffic. And this is exactly what we're going to see now, how service meshes allows us to, or enable us to use some kind of patterns or features to be used to make our life as developers easier. So the first group of patterns or features that we're going to see is that release patterns or traffic manipulation. First one is the well-known blue-green deployment. Probably all of you knows what is blue-green deployment. You've got your public traffic that goes to service X version 1, and then you just want to switch to service X version 2, you just change the route, and then all the traffic goes to service v2. Of course, you do not undeploy the version 1. So if you detect any problem in the new version, you can just switch back to the old version. Nothing new. Another pattern is canary release. Instead of doing an all or nothing release, what you are doing is just sending 90% of the traffic to v1, 10% of the traffic to v2. If we see that the v2 is behaving correctly, then we start increasing this traffic. So you're sending the 20%, 25, 50, 70, until you just send all the traffic to this new version. The other one is dark canaries. This is a new pattern, let's say, that it's similar like canary releases. But notice that in canary releases, you are just sending traffic, all your public traffic, without any kind of filtering. In case of dark canaries, you can filter the traffic. So you are saying all the traffic goes to V1 except all the traffic that the source is this IP. So for example, you could have an agreement with any of your clients to test or to use the latest and greatest thing. So you're just sending the traffic of this client to the new version. Meanwhile, the rest of the clients goes to the old version. This is another, for example, Facebook is doing the same thing for testing Facebook. Because if you are an employee of Facebook, what they are doing is just detecting that you are an employee of Facebook, and they are sending you to the latest version instead of the one that all of us are reaching out. Another pattern is shadowing traffic. Shadowing traffic or mirroring is sending the same request to two services at the same time. But there is a big difference here. Notice the arrows. You're sending one request to both of the services, but the request that goes to service V1 also produces a response, and this response is sent back to the client. But if you see the second one, the one that goes to the service V2, so the newest service, it's just a unidirectional arrow. This is what is called a fire and forget request, because you are sending the request and you don't care about the response. And I know that some of you might say, and why are you explaining me this? Why it's useful? And the reason that this is useful is because you can use the public traffic to test the version V2. So now you can only send one request. You start monitoring both services, because at the end, you have the same request, so you will expect similar response. And if there is an error, you can react to this error before releasing to the public traffic. There is another one which is called future graduation. This is one pattern that we use in Red Hat in several places, which basically says that, okay, the user itself has a profile tab, right? Or where you can choose how confident are you with the product. So if you are really confident with the product, you want to try the experimental things. So the experimental things is the latest or the newest version of the service, the V3. If you say, okay, yes, I feel confident and I want to try the latest things, but with some control, then you go to the beta, for example. And if you is a standard user that you want the things that are really tested and are in production, then you send the traffic to production. So basically, what we are doing is just creating a cookie with an ID, and depending on that ID, we are sending traffic to any of these services. But notice that it's called graduation. This means that we graduate the services. How? For example, suppose that the V3, we have been receiving a lot of traffic, we check all the monitoring system, everything works as expected, and then what we do is a promotion of all these services. So basically we're doing something like this. Now there is no experimental, and the beta goes to V3, and the V2 is the new production. So we are switching up. We're graduating all the services. And another one, which is fairly new, is creating a multi-tenancy or multi-tenancy pattern, which is dealing with the multi-tenancy problem from the point of view of the mesh. So instead of putting in our code things related to the tenant, we are just sending one request, one client sends a request to our service X, and then when the service X needs to go to DB or any of the DBs, they just send the traffic to the DB of the tenant. What it means is that with your pod, always connect to your database host. It's always the same host, right? DB, for example. But it's the mesh who is responsible of sending this DB to the real DB host. So you as a developer don't need to take care about the tenant. It's just something that is managed by the mesh. This for releases, but then let's see about resilience. We have talked about that we need to make our services resilient because we are in the network and the network is not reliable. So let's see how the meshes helps us on this. The first one, really easy, retry. You just do a request. If it fails, you do an automatic retry, or in this case, the mesh does an automatic retry. And then if it works, then it returns a response. And if not, then it returns the real error. Of course, you can configure if you want 1 retry, 3 retries, a sleep between retries, etc. But this is the idea of the retry pattern. Another one is the bulk hit. Usually, what happens is that you've got a service and you're sending a lot of requests to this service. But maybe you as a developer can see that, okay, I know that I can receive 1,000 requests concurrently, but no more. If I send more requests at the same time, then I'm sure that I'm going to have problems, and this pod will start behaving incorrectly. For this thing, for this reason, there is the bulk ahead pattern, where basically what you're just saying is how many concurrent connections I can do to this service. So you can put 1,000 concurrent connections. You put it. If you have 1,001, this one connection will wait until there is an empty slot to do the request. So it's a really safe way to protect that you don't overloading your services. Another one is the well-known circuit breaker. Again, probably most of you know circuit breaker, which basically is a pattern that allows you to detect errors. And if there is the number of errors rises above a threshold during a period of time, then the circuit is open. The circuit is open, it means that no more connections will be produced until some time. It's similar to bulk ahead if you wish, but the bulk ahead is more like about concurrency, and the circuit breaker is about the errors. Another one, this is probably you have not know about this, is the pool ejection pattern. If you know how Kubernetes works, basically you've got, usually when you scale up, you've got several pods of a service. So you've got service X, and then you have service Z, for example, with 4 pods of service Z. So when you do a request there, Kubernetes will choose the first pod. If you have another request, it will choose the next pod. If you have another request, next pod, and so on. So it's a round-robin approach. But the thing is, like, what's happened if one of these pods start behaving incorrectly, right? It start sending errors. Then, from the point of view of the mesh could say, or could act in the next sense. Is like, if I know that this pod is not working correctly, why am I still sending requests there to that pod? Maybe I could park. So they grab this pod from the pool of pods, and they put it and they park. Park until some time, maybe 5 seconds. After these 5 seconds, then the mesh will say, okay, let's see if now you are behaving correctly. Maybe you are behaving incorrectly because you've got a lot of traffic there, a lot of jobs to be done. Or maybe you were recovering from some kind of error. So then it put it again to the pool, and this pod will again start receiving requests. Another one releases a request timeout, where you can set a timeout on any request. So you said, okay, I want to do a request, and if it takes more than 1 second, just send an exception. Don't wait until this service gets you a response. Of course, you'll see it in the demo time, but the winning solution is doing retry plus pool ejection. With just these 2 approaches, you're solving almost all the problems that you get. Because notice that when you get an error from a pod, you're going to remove this pod, so it's not eligible anymore, and the request that was failing, you're going to be retried. And probably this retry will go to a pod that is behaving correctly. And then you will get a response. So you're treating the errors in a way that your client will never notice it. Another one that's, the family of patterns that you can use in the meshes or you can implement is about security. As I said, some of the attackers, what they are doing is not attacking the outside of your cluster, but from inside the cluster. So they go into the cluster and then they start let's say, sniffing all the traffic that happens across the mesh. For this reason, if you read in internet, you will see that your internal traffic should be encrypted as well. Since service meshes works at network layer, it's something that you do not need to deal in your services. Your services should go in HTTP, and it's the network layer responsible of encrypting this information. This is exactly what the mutual TLS pattern does with meshes, just encrypting under the cover all the network. Another one is, for example, rate limits. This is another way of securing your services against some attackers. For example, you can say that if the request comes from an anonymous user that you have not registered in your system, then just apply some kind of rate limit. So you can try to avoid having some kind of denial of service. Of course, this is not only the thing that you need to do to avoid the denial of service, but at the end, all the security is about onion, right? Putting layers and layers, and this is one layer that you can use. Another one is the authentication for services. Again, if you are into a microservice architecture, which security for authorizations are you using? Probably GWT or JOT. So it's basically sending tokens. But notice that again, these tokens is something that happens at network level. It appears in your architecture because you are using microservices architecture, not in a monolith. In a monolith, you don't need any token at all. And then it's something that it's in the network level. Then why not leverage meshes to deal with all this stuff related to tokens? For example, validating the token, verifying that has not been corrupted, verifying that has not been intercepted, verifying that has not been expired, verifying, for example, that you have a role inside this token, and this role is a valid role inside my system, and you have the rights to access to my system. All these kind of things that usually we put it inside our code is something that you should put it on the network layer. And another one is the black-white list. This is one pattern that I really love, which allows you to avoid any, let's say, developer by error or any attacker can start navigating through your mesh. So you're just doing a black or white list, just putting what is the correct way to communicate. So it's service 1 to service 2 to service 3, and what are the non-valid communication. For example, you don't want to communicate from service 2 to service 1, or from the service 3 to service 1, or the service 3 to service 2, or from outside to service 2 or service 3. So if you put this at the mesh layer, you implement this pattern inside your mesh, then you are securing all your communications, not from being intercepted, but to be able to, produce some kind of unwanted request. Observability is another thing about microservices, and of course, meshes can help you on this. The first one is about metrics. So since the network, everything happens in the network, it's really easy to, by default, getting metrics. We unify logs. The mesh knows exactly what's happening inside the network, so it's really easy to unify all the logs. Also, distributed tracing. Probably you're using Jigger or Zipkin, so this is something that could be provided by default without doing anything. And finally, one pattern that you'll see now that is called that I called it the mesh. And when I say the mesh, is that usually when you are doing microservice architecture, and when I said microservice architecture, I mean real microservice architecture, like 100 services deployed. Probably then what you want to see is have a global overview of what's happening inside your mesh. The final one is testing. You can use meshes to test your application. The first one is pod virtualization. Usually, when you've got all these services deployed, and then maybe you deploy a new version of the service, the version v2, and you want to test before opening to the public traffic. So what you have is like a special user that when it connects to your cluster, it goes to this new version. We have seen this when we were seeing the release patterns of the traffic, right? But now what's happened is that this new user is going to create a test, and this test, maybe it's an automatic test or maybe it's a person, going to try to test all the microservices that depends or that calls this test. So it's really annoying when all these services has some kind of side effects. Stateful services, for example, you start doing things that might be wrong. Just think about, for example, that is a shopping cart. You may end up by buying something because of a test. For fixing this, there is a pattern that I call pod virtualization, which basically you put it inside a pod, any of these service virtualization systems, like for example Overfly or WireMock. So you are recording some canned answers to some requests, right? And then you deploy this as a virtual pod. And then all the requests are sent automatically to this virtual pod. So you know that there will be no side effects on your architecture. And the same happens with the database. What's happened if my service B1 and service B2 are inserting things to a database? Then you might have a problem because you are start populating data inside your database. So to avoid this, you can just use VirtualDB, some technologies like, for example, JBoss State, which is an open source project. You can just change how things behave. So you say that when it's an insert, you go to a throwaway DB, so you deploy a throwaway DB. And when it's a select, you just go to the real DB. So then you can just start testing your application just using the real data, but you know that when it's going to be an insert, it's going to go to a database that it's going to be a stop when you finish your test. Then we've got fault injection. You can start doing random faults on your applications. For example, adding some HTTP error codes, or for example, injecting some delays on the communication and see how your application behaves. And finally, there is this multi-environment. I know that I would say most of the companies love this. Although I don't like having multi-environments. Probably all the companies, you have a QA environment, a staging environment, and a production environment. What you can do with the service mesh is creating a multi-environment pattern, which basically makes you deploy in two different namespaces, the QA environment and the production environment. And depending on some, for example, cookie or some request parameter, for example, user equal dep123, then you send all the traffic to the QA cluster. So now you're testing your application inside your production cluster, but having the traffic really split. So let's go to see some demo, just to aware you that most of the people or most of the demos you'll see with service meshes are just from hello world things. So I'm sending traffic here, sending traffic there, I do canary release, and these kind of things, which are really simple. In here, we're going to see really advanced topics. We're going to use Istio. Of course, it also works with any other service meshes, but in this case, I'm using Istio. So let's see how this works. Let's start. And okay, Nathan. Change. Okay, now, okay, this is, probably you don't see. This is my service, or my application that is deployed in a Kubernetes cluster. Here. Pods. Okay, you see that there is customer, there is a preference, and then there is recommendation B1 and recommendation B2. And as you might think, is like customer calls preference and preference calls recommendation. I can do a curl, and you see that I'm calling customer preference recommendation B2, and then if I do another curl, I'm calling customer preference recommendation B1. So just a round robin approach where I'm sending first to B1, then to B2. Now, let me scale V2 to have 2 replicas instead of 1. So now I've got service v1, service v2 with some host name, and service v2 with another host name. Again, if I do the call, you'll see that I'm getting v2, v2, and v1. Notice that's important, this is the host name. In this case, this is 9W and this is VR. And now this is the v1. Now, I can go here, I can start K9S, and I'm going to go to this 9W, and I'm going to change one thing. And I'm going to do a call to localhost 8080 misbehave. Basically, what I'm just saying is that now I want that this version of this service, I want to return a 503. Of course, I can do a call localhost 8080 minus BBB, and you see that it's returning a 503. Now, what's happening if I do, remember that I've been doing calls here, and you see that I'm getting B1 from one host, B1 from the other host, and B1, B2, B2, B1, sorry. Now if I do a call, I'm getting B1, and now B2 from the BR host. I do a B1, and then another time B2 with BR. So the failing pod, which is the one which is the 9W, is never serving any request. And the reason is that it's returning an error, so I'm just doing a pull ejection of this pod and retrying again. For this reason, that the user never noticed that this pod is not working correctly. Now, if you want to see that this is how I'm saying, I can do a 8080 behave. Now it returns again 200, so I can just start doing calls. And now you see here that there is the version v2 with the 9W. So this is a really nice way to make your services resilient without having to touch anything in your code. Another thing that we can do, as I said, is the MTLS. Let me go here. This is customer. I'm going here. I don't know if it's, yeah, it's going to work. Now, oops. Let me copy one thing. I'm just, what is the IP? 25, wait. Okay, now I'm sniffing all the traffic that goes from this pod to another pod on its, or comes into from another pod, right? Now I have no MTLS. Notice that I'm not redeploying anything. My services are the same services, which if you want to know it, they are using HTTP. I can do a curl, and if I see what I've now, you see that all the traffic is not encrypted. You can see all the headers, and then here all the content in binary. Now, let's apply MTLS stuff. I can just do kubectl create Istio files. Authentication enable TLS. So I'm just enabling TLS across my mesh. So I'm just saying I want to use TLS or MTLS in all my communications inside the mesh, and then I need to configure in which services I want to apply it, which is just a matter of applying another destination rules TLS. Now I've just said all the communication that comes in the customer preference recommendation services, I want to be encrypted. Now, remember here, I can do this. Now I do a call. And notice that now everything is encrypted. You don't see any header. And the good thing is that I've not redeployed anything. I've not touched my code. My code still works in HTTP, but the communication goes in HTTPS. So it's a really good feature to have into consideration, because now as a developer, you don't need to deal with these painful things of certificates, key chains, and so on. So it's a really nice thing to have. Then let me finish, or let me clean everything. Now, again, I'm just working in HTTP. And let's try the token. I'm going to apply another resource here. which is the end user authentication. So I'm just enabling GWT on my mesh. So basically it's saying, if you don't provide me a valid token, I'm not going to allow you to communicate between or inside my mesh. So now I can do a curl again, and you see that says origin authentication failed, because now I'm expecting a token, I'm not providing a token, so the mesh refused the request. Now I have here a token, and now I can do a curl -h, sending this barrier token, and now of course it works. Realism. Notice that I'm not touch my code. I'm not redeployed the services. It's just the mesh who takes care of these things. Then suppose that I want to do a role-based access control thing. So my customer service can only be reached by a user that has in the token a role customer. The only thing that I need to do is apply other resources, which is the authorization, enable airbag. So I'm just saying, notice that I want to use a role-based access control, and create -f, Istio files, namespace, policy, GWT. Now what's happening if I do a curl again? It's failing, because my original token does not contain a role with customer. So I just need to go here again. I copy one token. If you're let's see if now if you want to see how this token looks like, let me check if it, let's see if we are lucky enough. Okay, meanwhile I can, now if I do a curl again, now it works. Because this token contains the role that has access to my services. And now I can go here, but okay. So as you can see, I can change the security constraints of my application without having to redeploy anything. Everything is managed by the mesh. And this is one of the important things of following all these patterns. I think that most of the service meshes implement all of them, but if not, it should be easy to implement, because at the end, everything is managed by a sidecar container. So you just need to start a sidecar container with a proxy and send all the traffic to this proxy and then implement these patterns. Let me see. No, this is not going to work. Okay, another, okay, if not, let's remove everything. Another thing that I want to show you is what I mentioned, of observability. My services doesn't know anything about Prometheus or Grafana or Kiali or I don't know, or Jigger. Everything is provided by the mesh. So I can go here and wait. For example, we can see Kiali in action. Kiali basically allows, it's an implementation of the mesh pattern that allows you to see what's going on inside your mesh. Notice that, I don't know if I do this. Oops. Okay. See that there is customer, preference, recommendation. Recommendation have B1 and B2. I can check this, the traffic that goes to B2. Well, in this case, we are just checking the last minute. So for example, I can display traffic and yeah, now if I start doing curls, okay. Now notice that I've removed all the GWT stuff, so now I can just do curls as usually without anything. And now notice how I'm seeing how the traffic is going. Go to V1 and then V2 and V1 at the same time. If I just do some different stuff, then all this stuff is, or all these ballots are changed depending on how the traffic behaves. The last thing that I want to show you is the shadowing traffic. To show you shadow traffic, you see that, let me scale down. Well, while I scale down, let me show you another thing first. And as I said, also you have Prometheus installed. So all the information that's happening inside the mesh is sent to Prometheus. And I'm going to show you this. Notice this graph. This is the RSS memory, which is the full memory that is used by the processes. Notice that here we have recommendation, which is like 80 megabytes of RAM required to run them. There are two, because there's recommendation V1 and V2. But notice here, this is preference and customer, which is like 15 megabytes. Both applications are in Java. One is using your favorite cloud-native Java stack. The second one is using Quarkus. Quarkus is an open source project that allows you to take your enterprise applications and compile them to native. And since you're compiling to native, you just need 15 megabytes of RAM. The applications are exactly the same. It's just a service that takes a request and sends a response. But notice the difference. One is Java running in the JVM with your favorite traditional cloud native stack, 80 megabytes. If not, you can just Quarkus and it's just 15 megabytes, which is pretty nice. And notice that I didn't know about Prometheus, but the mesh takes care of all these things for me. And now probably this has ended up by scaling. Yeah, let's see. I have V1 and V2 again. Let's do mirroring traffic. I'm going to exit here. I'm going to refresh. Okay, I'm going to V2, and I'm going to check the logs. Notice that the last request that has been sent to V2 is the number 21. Of course, I can do a call. This is V1 and this is V2, and now I have here a 21. Let me do kubectl create -f Istio files destination, and now I'm going to apply the mirroring traffic thing, which I think that it's virtual service v1 mirror v2. So now I'm sending the request to v1 and v2. The only response that I'm going to receive as client is the v1, but the v2 is also receive this request. I'm going to do a curl. Remember, the last one is the 21. This is the last request that I've received. I will do, for example, one curl, another curl, another curl. All the time I'm getting the v1, no v2, but now see here that I'm getting the 24. So the requests are sent to both services, but just the response, the valid response, comes from the v1. And we are almost done. Let me undo this. So of course, probably you will say, yeah, that's pretty nice, but I want to learn more. I want to learn how you've done all these things. These are the links. bit.ly/Istio tutorial. You will see how to install Istio in your Kubernetes cluster, how to deploy all my customer preference recommendation example, and then I start applying these techniques that I've shown you here, but also new ones like blue-greens, or I mean, at the end is all the patterns that you have seen explained in the slides. There are explained on how you can implement it in Istio, how you can apply them in Istio. And that's all. Thank you very much. There is anything, any question, just send me an email if you want, or a tweet. Some people ask me, but can I really send you an email? And it's, yes, of course you can send me an email because it's their email. If not, I will remove it from the slide. So if you have anything, mail, Twitter, or I will be around the venue today. Thank you very much.